Hello, everybody. Thanks for coming to my talk, and I'm delighted to be here at USENIX. My name is Andrei Costin, and I'll be presenting our work titled A Large-Scale Analysis of the Security of Embedded Firmwares. As presenter, my co-authors are Jonas, Zaddach, Aurélien, Francillon, and Davide, Balzarotti. We did this work at Eurecom. So today, embedded systems are everywhere, and we interact with embedded systems on a daily basis more and more. And as such, embedded systems are computer systems with a dedicated functionality, such as routing packets, printing pages, making VoIP phone calls. On top of this, the embedded systems are getting smarter and more complex. They are providing various administrative and non-administrative interfaces. They implement complex software systems. They implement complex protocols and process various types of data. And the software and data which supports the functionality of an embedded systems is the firmware, which is the focus of our research. In addition to that, the embedded systems are getting heavily interconnected via private and public networks into what some people call the Internet of Things, which is basically nothing more than a large-scale, heterogeneous population of embedded systems, and not only. However, we have seen and we keep seeing many examples of insecure embedded systems on a daily basis, including routers, printers, VoIP systems, cars, drones, and the list could go on for more dozens of minutes because of the variety of embedded systems and their deployment. However, as we can notice is that each of the above examples is a result of an individual analysis or an individual research, and it many times include manual and tedious efforts, and we can see that it doesn't scale very well. So we propose ourselves the goal of performing a large-scale analysis to provide a better understanding of a problem. However, large-scale analysis comes with several problems, and one of the problems is heterogeneity. Heterogeneity of hardware, architecture, and operating systems used in the device and the firmwares, and also the heterogeneity of intended users and the requirements for the devices, and finally, the heterogeneity of security goals put in front of each firmware and device. In addition to that, manual analysis doesn't scale because it requires finding and downloading the firmware files, unpacking and performing the initial or subsequent analysis, and rediscovering the same or similar bug in other firmwares. So there were several previous approaches. One of them is to use testing on real devices, which yields really accurate results, but doesn't scale very well because it involves physical devices, costs, logistics, and management. The other approach used the scanning devices on the internet, and some authors did large-scale testing. However, it can only test for known vulnerabilities, for example, like default passwords, and basically it provides a black box approach. And sometimes doing more is too intrusive, basically being close to unethical or unethical, where some researchers anonymously had to inject code in compromised devices, hence attacking the devices themselves for their study. So our approach to the large-scale analysis is to collect a large number of firmware images, perform broad but simple static analysis, and finally correlate across firmwares the findings or results. So it brings us several advantages among these being that we don't do intrusive online testing, and we have no device involved at all in our experiments, and it's fully scalable in terms of hardware resources, computing power, and money. However, it also comes with many challenges, as we can see forward. An important observation is that the mainstream systems have centralized updates, where the updates channels and formats are well understood and very well established. On the contrary, the challenge for embedded systems is that there is no centralized updates, where a firmware update or a firmware recovery or dump involves a combination of various tricks, including building schematics, using development or breakout boards, using or writing custom drivers or custom utilities. So hence, having no centralized update mechanism is that we don't have a centralized database for firmwares. So it means that we have to start collecting a data set because there is no large-scale firmware data set available yet. And it is contrary to what happens in other computer science and research areas, including security, where there are well-annotated large data sets. So we collected a subset of the firmware available for downloads. And this is only a subset because many firmwares are not publicly available due to many effects, such as not intended to have an upgrade at all, or some requiring a purchase or a registration of a product, which again is not according to our methodology, which is deviceless. This is why we have a firmware.re project, which I'll present a little bit later. So after collecting the databases, the firmwares, and a large set of files, we have the following challenge, which is firmware identification. There are a set of files which are clearly a firmware. It is a Linux-based system and so on. For an ARM architecture, for example, there's clearly a set of files which are clearly not a firmware, like PDF documents, documentation, images, release notes, and so on. But there is also a big chunk, which is the gray area in the middle, which is uncertain. And a good example for this are the printers, where a firmware upgrade on the printer is performed by printing a specially crafted PostScript document. So at the first glance, it's a PostScript document which you would discard, but it performs a firmware upgrade. So it falls in that uncertainty area. This means that we cannot naively discard certain types of files, and we have to basically unpack files we collect until certain points. But unpacking brings us the next challenge of unpacking in custom formats, how to reliably unpack and learn the formats. So building upon the previous example, we can see that the vendor had provided a zip file as a firmware package. Inside the zip file, there is an executable file and a PostScript file. And a naive approach would discard the PostScript as a document file and focus on the executable file. The executable file would have to be run, or in case it's a self-extracting archive, would have to be extracted even more, not to be run. And it would turn out as a dead end because there's a device driver inside, which is not interesting from our perspective. On the other hand, following the PostScript document and following the ASCII-85 data streams, which encode various pieces of data inside PostScript and PDF documents, we can decode the data and we can find actually pieces of ELF files which are intended to be a complete embedded software system. It is intended to be an executable performing the final upgrade on the device, for example, the printer, or it can be just a small firmware patch. Moreover, often a firmware upgrade is just a simple data blob. It has no headers, no known format, and it appears just as a data blob, binary blob, or ASCII blob. So our approach to unpacking and custom formats challenge is we compared several existing tools, and we used BAT tool, which stands for Binary Analysis Toolkit, and we extended it with multiple custom unpackers on top of the default ones which come shipped with the tool. But again, it is a continuous development because of a myriad of formats and vendors involved. So because often a firmware is just a data blob, we have to do file carving in order to give more chance of extracting something from the file. And file carving basically involves brute forcing at every offset with all known unpackers. Which brings, and we also have to know and have to build heuristics for detecting when to stop carving and unpacking, because it can result in lots of false positive and noisy data. So brute forcing and file carving brings us to the next challenge, which is scalability and computational challenge, because unpacking and file carving is very CPU intensive, and we want to use this CPU power wisely. At the same time, unpacking results in millions of unpacked files, and it clearly shows that manual analysis is infeasible. And also, tasks such as one-to-one fuzzy hash comparison on a dataset of tens of millions of files is clearly CPU intensive and is unfeasible to do every day or all the time. And the last, given if we find the issue, is the challenge of results confirmation. So an issue which is found statically may not apply to the real device due to various settings or some other issues and cannot guarantee exploitability. A simple example is that we find statically a vulnerable daemon, but the daemon is never started by the init scripts, for example. So issue confirmation is a difficult problem, and it requires advanced analysis, both static and dynamic, and it often requires real devices for final confirmation. And as we can see, involving multiple types of analysis and devices, again, does not scale well, especially in heterogeneous environments. So finalizing with the challenges, I want to give you an overview of our architecture. So we have the internet, where we know there's plenty or almost plenty of firmwares, and we have a crawler, which crawls the internet for firmwares and stores them in a data store. Additionally, we provide a public web interface where the users or researchers can submit their files, just in case our crawlers wouldn't have access to them or just miss them because of the search queries. Then our system takes the firmwares from the data store and sends them to the firmware analysis cloud. In our particular implementation, because it can vary, it consists of a master node, which basically takes each firmware file and sends for CPU-intensive processing to multiple nodes. And such processing includes unpacking, static analysis, fuzzy hash computation and correlation, and credential or password hash cracking. After getting all this data, we put it in a separate database for further reporting and analysis, and we provide a short summarized data to the uploading user in case the user uploaded. And finally, we also do two more processing steps, such as data enrichment, which can help us derive more information, such as product, device, or vendor and release date, and also running correlation between the firmwares. So our crawler collected around 800,000 files, summing up 1.8 terabytes of data. And we used two main sources, such as FTP indexing engines, and results from Google Custom Search Engines API, where submitting firmware download keywords reveals a set of URLs where most likely firmwares are available for download. Additionally, as I mentioned, we provide this project firmware.re where users or researchers can provide the firmware. We provide all our infrastructure tools in our private cloud, and then it will provide back the unpacking and result of analysis. So a summary of the unpacking looks like starting from around 800,000 collected files, going through the filtering stages, random selection of the files because we couldn't process all of them at time of submission, and then unpacking and all other processing, we ended up with around 1.7 million of unpacked files. Subsequently, we run static analysis on all these unpacked files, and this static analysis includes correlation and clustering based on fuzzy hash, and it's important to note that we also store the fuzzy hash for each unpacked and processed file, so we can do the correlation later. We also have the private SSL keys, credentials. We statically check for simple misconfigurations, such as web server misconfigurations, credential or hard-coded credentials, and code repositories. And we also have static analysis in terms of data enrichment, searching for version banners and specific keywords. A quick example of correlation is via fuzzy hashing is as follows. Given a firmware and a vulnerable file inside it, we basically take the firmware as such. We build a small subgraph of all the firmwares and inner files which relate to the original vulnerable firmware, and then we take the vulnerability and can propagate via similarity scores. As you can see, there are two files which are 99 and 95% similar by fuzzy hashing. So we can assume that these files could be vulnerable and should be looked more closely afterwards, or advanced techniques be applied to. Another example is the RSA keys, where we started from a private RSA key we extracted from a vendor. And then we took this RSA key, the self-signed certificate, and normally for a secure device, a sane choice would be that RSA keys, private RSA keys, would be regenerated on first boot. Then we took the fingerprint, we looked up the fingerprint of the SSL certificate and the private key in the ZMap's HTTPS survey database, and surprisingly, it returned 30,000 online IP addresses, online devices, just for one key. Then we were surprised, however, randomly looking at these IPs revealed that not only these IPs are responding to requests, some of the IPs actually provide pages for a second vendor, which we didn't have the firmware from. So what it means is that these two vendors and these two devices are using a white label approach where a device is coming from a common vendor and has common vulnerabilities, might have common vulnerabilities. So in summary, we discovered 38 new vulnerabilities, and we correlated them to around 140,000 online devices, and estimate that 700 firmwares, around 700 firmwares are affected by at least one of these vulnerabilities. So contributions, we did the first large-scale static analysis of firmwares, and we described the main challenges associated with this activity. We shown the advantages of performing a large-scale analysis of firmware images, and we implemented the framework and several efficient static techniques, yet simple but efficient. So as conclusion, a broader view on firmwares is not only beneficial, but necessary for discovery and analysis of vulnerabilities. And correlation reveals firmware relationships. It allows to show how vulnerabilities reappear across different products or vendors. And it could allow seeing how firmwares evolve or get fixed. We estimate there are plenty of latent vulnerabilities due to old software. And security comes as a trade-off with cost and time to market. And clearly, it's not a priority for some of the embedded vendors. Thank you. And if you have any questions, I will be glad to take them.
Regarding the database that you're going to make available, are you going to try and work with the vendors more so that additional information will be available for some of the more obscure firmware?
That's a very good question, thank you. Actually, we provide some of the data which we can make available on our website under USENIX security section. And yes, we are following responsible disclosure, and we are trying to work with certs or vendors directly, reporting the vulnerabilities. Some of them do not respond, unfortunately, but those who respond, we try to provide all the information. And we also started rolling out some of the details of the vulnerabilities on our firmware.re/usenisec14 section.
I was wondering, in your analysis of firmware that you've done so far, have you done any work with regards to characterizing what's the vulnerabilities that are found in third-party libraries versus, say, the custom firmware that would be driving a board, say? So stuff like, for instance, if you were talking in Linux world, like libpng, all those kinds of third-party libraries.
Okay, thank you for the question. We are collecting data on all the standard binaries as well, whether they have symbols or not, the libraries, library versions. Unfortunately, we didn't do at this moment an analysis of the specific versions and whether it has a vulnerability or not. And this is due to several things. First, having just the library version gives just a clue, but it doesn't give a guarantee that the firmware is vulnerable, because it can be built with different settings. It can be, the architecture might make it invulnerable, and many other factors would make such conclusion too broad to say. But yes, this is one of the things we collect, and we are looking forward to do this, but on a more research correct way of inferring this kind of information.
This has to be quick, with a quick answer.
Adam Drew from Qualcomm. I was wondering if you had a feeling for what, you gathered firmware images from sort of scanning the internet. Did you have a feeling for what percentage they covered of, say, fielded devices? There's a whole lot more out there that you may not have images for. Do you have a feeling for what sort of percentage coverage you got for your set of firmware images?
This is a very good question. This is the question we try to ask ourselves as well. The true answer is that we don't know, because there is no reference firmware dataset, and there is no well annotated data on how many devices, embedded devices, are out there produced by how many vendors. And it is really hard to estimate just by some numbers without having some more inputs in this regard. We try to estimate, but the true answer, it would be like non-representative unless there's a reference data for this.
Well, thank you very much.
Thank you.